When you see a plus sign, think of an OR gate, not normal math. When you see a dot, think of an AND gate. Now, here's some of the rules about Boolean algebra.
This is like learning a middle language.
A plus 0. If you have an OR gate, one input is 0, the other one is A, what is your output going to be? A. Why? It depends on what A is. If A is 0, what is 0 or 0? 0. If A is 1, what's 1 or 0? 1. So it depends on A. If you have A plus 1, if you have an OR gate, I already made one leg 1. That's always going to be 1. Doesn't matter what A is. One of the inputs is already 1.
Wait, why doesn't it matter?
Because one of the input is 1. An OR gate, once one input is 1, the result is 1.
If A is 1, then it's 1 or 1, so then that's 1.
Well, that's 1. If A is 0, 0 or 1, still a 1.
You can only have 0 or 1.
Yep.
We're not going higher than 0 or 1.
Yeah, no, that's the rules.
Yeah.
Gotcha. Okay, I get it now.
3. Anything OR it with its complement.
A.
Try again. 1. When A is 0, what's the complement? 1. 0 or 1 is what? 1. If A is 1, what's 1 or 0? 1. That's always a 1. Let's put some AND. AND gates. A and 1. A and 1. When A is 0, what is 0 and 1?
0.
When A is 1, what's 1 and 1?
1.
So it depends on A. If A is 0, the result is 0. If A is 1, the result is 1. What is A and 0?
0.
That's 0. Yep. What is A and A not?
0.
0. Very good. And if 1 is 1, 1 is 0. The result is 0.
Question.
Yes.
What does A not stand for again?
The complement.
Complement.
So if this is 1, that's 0. If this is 0, that's 1. What is A or A? Still A. When A is 0, what's 0 or 0? 0. When A is 1, what's 1 or 1? 1. At the same token, what's A and A? A. Yep. What's A complement? Complement. Yep, double complement of something. It's like double negative. It makes it what? Positive. It goes back to original one. That's really A. Because if you think of A is 0. Let's use a 0. What's the complement of 0? 1. What's the complement of 1? It goes back to 0. When A is 1, what's the complement of 1? 0. What's the complement of 0? Back to 1. So a double complement does nothing.
Cancels itself out.
Yep. Just like two minus signs makes a plus. And the distributive property, you know this from math. This is rule number 9. 10. If you have A parentheses B plus C, we know that from math. That's what? Isn't that AB plus AC? That's still true. The one that people get hung on it, this one, I'll make a different color. That's a big one. This one's equal to that.
Can it go the other way?
Yep. And why is this equal to this? Well, let's look at the math behind it. Let's go and derive that. We know how to use the FOIL method, right? Remember the FOIL method? I drew a pen. I don't know if you can see the pens. I try to make them light. Oh. Yep, that's correct. So let's do the FOIL method on it. Let's see what will happen. A times A. What's A and A? A. A times C. AC. B times A. AB. Right? And B times C, which is what?
BC.
BC. Let's look at the first three. What do they have in common?
Love an A.
Take an A out. What's left? 1 plus C plus B. That's an OR gate. You already got a 1 here. Any OR gate, once you have a 1, the whole thing is going to be what?
1.
1. So that's A and 1. And A and 1, where is it? Right here, which is what? A. So that's why that's equal to A plus BC. So A plus B times A plus C is the same as A plus BC. So let's go back to that problem that we just finished designing. Where was it? And see if we can simplify that. Remember that ugly one? This one here? That just cost us $6-7 to design. Let's see if I can simplify that. Here's the problem. Let me write it down again. The problem was W bar X, Y, Z bar plus W, X bar, Y bar, Z bar plus W, X bar, Y, Z plus W, X, Y, and Z. Can I simplify that design? Well, let me look at the first two and the last two. Let me just make sure I copied it right. W bar X, Y, Z bar, W bar X, Y, Z bar, plus W, X bar, Y bar, Z bar, yep, plus W, Y bar, or X bar, Y, Z, yep. Okay, let's look at the last two. I see something quickly in the last two. Look at these two. What do you notice in them?
W1 X bar.
So I can factor out Y, W, Y, Z out. What's left if I do that? X bar plus X. What's X bar plus X? 1. WYZ times 1 is WYZ. Looking at these two, I'm not much help here. But do you see any help there with that one?
And just the Z bar.
Well, I can't. The Z bar, because this is Y bar, doesn't match. These guys don't match, right?
I think you can do is take out a Z bar.
Yeah, but that doesn't really help me much.
Yeah. So would you do a different combination then?
I could do a different combination if that doesn't work out. What are you thinking about?
What combine the middle ones and then the outside ones?
Well, the outside ones, I have two unknowns. See W bar and W and Z bar and Z. That's not a 1, by the way. So Dave's saying, how about these two guys? So if I bring the other two back, so that's where I am so far. So instead of having 4 terms, I'm down to 3, and this has 3 input. And I'm looking to find anything. I see a W. See, what can I do here? What can I do here? Let's see. Let's look. W. I got a Y here. A Z. Y and Y bar won't help me. Z and Z bar. Z bar here. I don't see much relief there to simplify it anymore. We shrunk a little bit, not a lot. So this one went from 4 to 3. So when you graph that, you got 4 of these. I mean 3 of these and 1 OR gate. This at least 3 input. Maybe I shrunk a little bit. Let me take a different example and see if I can have a better one. If I can steal a problem from the book there. Let's take one. Okay. Let's look at this one. I have X bar, Y, Z bar, plus X bar, Y, Z, plus X, Y bar, Z bar, plus X, Y bar, Z, plus X, Y, Z.
But you can take the x bar y z bar and pair it up with the x y bar z.
Which one? Number wise, which one are you looking at?
1 and 3.
1 and 3?
Yeah. Sorry, 1, 2, 4. Sorry.
How about 1 and 2? 1 and 2 is easier, it's right there next to each other.
Oh, okay.
Look at 1 and 2. What do you notice there?
They both have an x bar.
You have X bar Y in them, right? So what's left? Z bar plus Z. What's Z bar plus Z? 1. This one X bar Y. Let's look at this. This group. What do they have in common? It looks like XY bar, right? Z bar plus Z. What's Z bar plus Z? 1. And the last one is still there. So it was 1, 2, 3, 4, 5 gates with 3 inputs.
Now we only have 3 gates.
Now 3 gates. The nice thing about this, I can fit these.
Two is one.
Huh?
You say the first two is one.
No.
Right there. That.
Nope. These two?
Yeah.
No. The question, can I say that's equal to 1? I can prove to you that's not 1 quickly. And the way you prove it, here we go. X and Y. Let's list the combinations for X and Y. We'll see what the result is equal to. Could have 0, 0. That's called the truth table, by the way. 0, 1, for those people wondering. 1, 0, and 1, 1. To prove that's really simplified. So let's find what X bar and Y is. First column. This is X, so the complement will be 1, right? 1 and 0, that's a 0. 1 and 1, that's a 1. This is complement. Now 0 and 0, that's a 0. This is 0. 0 and 1, that's a 0. The other one, X, Y bar. Let's see what that column looks like. It says complement this. That becomes 1, 0, 1, 0. 1, 0, 1, 0. What's 1 and 0? 0. What is 0 and 0?
0.
0. What is 1 and 1? 1. What's 0 and 1?
1.
And
Oh, 0.
0. And now let's add these guys together. Because the question was, isn't that a 1? Take these guys and OR them. 0 or 0. 1 or 0. 0 or 1. 0 or 0. It's not a 1. We do have a gate called exclusive OR that gives us that. If one of the input is 1, you get a 1. If the inputs are the same, you get a 0. We have a gate, but we didn't cover it yet. So we do have a gate that will give me this.
So what would it have to equal for it to be, it would have to equal 1, right?
Everything has to be 1 for the result to be 1.
Okay.
This has to be 1, 1, 1, 1. If they're all 1s here, then he's right. That simplifies to a 1.
What if they're all 0?
Then that's 0.
Yeah, it have to be the top.
Your output will never be 1. You know? So now the question, can I go back to this one and simplify this anymore? Can I put these guys together? Probably not. But the good news is, assuming I have the complement, notice I have a chip that has 4 OR gates on it, right? I can use this one to get that. I can use this one to get this. I'm going to take the result now and OR it with I don't have room here, so I'll go like this. I don't have room on the bottom of it. With another OR gate of how many inputs? 3. Since I'm using a 3 input, I have to use 1 here. I don't really care.
Right? That's or.
That's OR. Yep, OR and OR both. So, oh, that's an AND. I'm sorry. These are AND. And now this is supposed to be an AND, but I got a problem. I got a chip that has 4 AND gate. I only use 2 of them. See that one right there? So what can I do? I don't want to have another chip with 3 input AND gate. It's funny how to draw from this side like it's so complicated for my brain. So instead of using a 3 input AND gate, since my chip has 4 of them, I already used 2 of them, I still have 2 free ones. I use the 2 free ones to make me the 3rd AND gate. That's 2 ANDs and the result with another one, and now all 3 OR together, and that's my function. Otherwise, I have 1, 2, 3, 4, 5. I will need 2, because it has only 3 on each chip there. There's 1 chip here. There's another chip here that's 2 3 input OR gates. 3 input AND gates. I need 1, 2, 3, 4 input OR gates. So I eliminated 1 chip with that design already. $1.50, $1.25 discount. You go, well, it's a big deal. There's $1.25. Go buy yourself an ice cream and something, French fries from McDonald's. $1.25 if it's an Apple computer. How many apples they sold last year?
Millions.
Yep, 25, 30 million times $1. About $35 million. Not a bad deal. You know? So you have to look at the big picture. We might be shrinking the design a little bit, but you could be saving millions of dollars. If Budweiser can save a penny on their bottles when they make the bottles, the cap, whatever it is, if they can save a penny, imagine how many bottles of beer they fill every day. I've been to Florida. They have that Budweiser place there. You see the bottles coming in a room like this full of empty ones. A minute later, here they come out on the belt. They're all full of beer. So if you can save a penny for each one of them, boy, oh boy. Look at the post office. They raise the price by what? 1 or 2 cents? You can have your 2 cents. Big deal. What's a 2 cents? 2 cents for one house. Like when you put 10 stamps per week, 2 cents, that's 20 cents. You can have it. How many million people are sending mails? That number becomes a gain of about 5, 10, 20 million dollars, per year. Oh no. Go away. One of my students.